The detection comes on an October night when the telescope array in Hawaii sweeps its automated gaze across a section of sky it has photographed 10,000 times before. The pixels register something new. A point of light moves against the fixed background of distant stars, its position shifting in ways that software flags as anomalous. Within hours, observatories on 3 continents confirm the coordinates. Within days, orbital calculations reveal what the light represents: an object passing through the solar system on a trajectory that originates from outside, from the space between stars, from a darkness that belongs to no sun. They name it 3I/Atlas, the third interstellar visitor confirmed by human instruments. The designation is bureaucratic, efficient, empty of poetry. It only took 4 billion years for someone to notice. The object moves through the inner solar system at 26 kilometers per second relative to the sun's rest frame. This velocity exceeds escape velocity. It will not orbit. It will not return. Its path curves gently around our star according to gravitational mathematics. But the curve does not close into an ellipse. Instead, it opens into a hyperbola, a shape that arrives from infinity and departs toward infinity, never repeating. Orbital eccentricity measures how stretched an orbit becomes. Circles have eccentricity 0. Ellipses fall between 0 and 1. Parabolas touch exactly 1. This object's eccentricity exceeds 1.2. The number is small but absolute. It makes the difference between captive and free. The light reaching Earth from 3I/Atlas has travelled for minutes, but the object itself has travelled for an age that dwarfs human history, somewhere in the Milky Way's spiral disk, perhaps 200 light-years away, perhaps 500. A star system shed this fragment into the galactic tide. Gravitational perturbations from giant planets, or near passes with neighbouring stars, or the slow drift of orbital dynamics over millions of years, any of these could have nudged it onto an unbound path. Once free of its birth system's gravity well, it drifted. Interstellar space is not empty, but it is profoundly sparse. Between stars, the density of matter falls to 1 atom per cubic centimetre, sometimes fewer. The object passed through this near vacuum in silence, in cold, in darkness broken only by the collective glow of billions of distant suns. It tumbled slowly. It cooled to within a few degrees of absolute 0. It carried no record of its origin except the chemical ratios locked in its structure, a signature written by a star we cannot yet identify. The astronomers note that its colour is slightly red. Reflected sunlight analysed through spectroscopy reveals absorption features consistent with organic compounds, with carbon chains, with materials processed by radiation over immense time. These are not signs of life, but of chemistry, the slow accumulation of cosmic ray impacts, the patient darkening of surface ices, the quiet weathering that occurs even in the void. Similar colours appear on Kuiper Belt objects, on the distant moons of Jupiter, on asteroids that have aged in the outer solar system's chill. But those objects formed here condense from the solar nebula's primordial disk. This visitor formed somewhere else, cooked in a different protoplanetary cloud, shaped by a different star's heat and light. Its chemistry is foreign in the gentlest sense familiar elements, arranged by unfamiliar conditions. It only took crossing 100 trillion kilometers to arrive at our instruments. The shape remains uncertain. Early observations suggest elongation, perhaps a ratio of 3:1. Length to width, it tumbles through space in a complex rotation, reflecting sunlight in patterns that brighten and dim over hours. Light curves, graphs of brightness against time show the irregular signature of a non-spherical body spinning on multiple axes. This tumbling is common. Small objects in space rarely rotate smoothly. Collisions impart angular momentum in random directions. Over time, the spin axes precess, wobble, drift. For 3I/Atlas, the tumbling began millions of years ago, perhaps during its ejection from its home system. perhaps from a collision in the dark between stars. The rotation persists because space offers no friction, no atmosphere to slow it. The object spins as it has spun for longer than genus Homo has existed. Its size is difficult to measure directly. Astronomers infer dimensions from brightness. But brightness depends on both size and reflectivity. If the surface is dark, absorbing most light, the object must be large to shine as brightly as the observed. If the surface is icy and reflective, it could be much smaller. Current estimates place its longest axis near 400 meters, roughly the length of 4 football fields laid end to end, roughly the height of a modest skyscraper, roughly small enough to be unremarkable among the countless fragments drifting through any planetary system. It is not rare in size. It is rare only in trajectory. It only took being unbound to become interesting. Ground-based telescopes track it nightly. Space telescopes, freed from atmospheric distortion, capture sharper images. Radio dishes listen for any signal, finding none. Infrared instruments measure its thermal emission. The faint heat it radiates is barely above the cosmic microwave background. The afterglow of the universe is beginning, still cooling after 13 billion years. The object is cold. Even as it falls toward the sun, gaining speed and beginning to warm, its interior remains at temperatures where nitrogen freezes, where carbon dioxide becomes solid, where water ice is harder than granite. These conditions have persisted for most of its existence. It has spent more time cold than warm, more time between stars than near any star, more time invisible than observed. The discovery triggers a cascade of observation proposals. Telescope time, always scarce, is reallocated. Researchers in a dozen countries submit requests for spectroscopy, photometry, astrometry. They want to know its composition, its structure, its precise orbit. They want to understand where it came from and what it represents. But the object does not slow. It does not pause for study. It continues its gravitationally determined path, indifferent to the curiosity it inspires. Humans have only a few months to observe it before distance and dimness render it undetectable. The window is narrow. It only took travelling across interstellar distances to become briefly visible. There is something quietly absurd about the detection. For billions of years, objects like this have surely passed through the solar system unnoticed, before telescopes, before photography, before human eyes evolved to see light. They came and went in silence. Even after the invention of astronomy, most of the sky goes unobserved most of the time. Survey programs scan only fractions of the celestial sphere each night. Clouds obscure, daylight blinds, technical failures interrupt. That this object was detected at all represents a conjunction of technology, timing, and the patient work of automated systems designed to notice change. A century earlier, it would have passed unseen. A century later, it will be light years away, unreachable. It only took happening to look at the right patch of sky at the right moment. The name 3I/Atlas carries its own small history. The I denotes interstellar, a designation created only recently when the first such object, Oumuamua, arrived in 2017. Before that, the classification system assumed everything detected belonged to the solar system, either a comet, an asteroid, or something bound to the sun. The discovery of objects that do not belong required new language, new categories. Atlas refers to the survey telescope that found it, part of a network designed to detect near-Earth asteroids for planetary defense. The system was built to find threats. Instead, it found a visitor. It only took looking for danger to discover wonder. The data streams in, numbers fill spreadsheets. Orbital elements refine with each night's observations. The uncertainty in position shrinks. The path becomes clearer. And beneath the mathematics, beneath the spectra and light curves and dynamical models, a simple fact persists: something formed in another star's vicinity is here now, passing through our sun's domain, visible for a brief span before returning to the dark between stars. It brings news from elsewhere written in chemistry and motion. The news is quiet. The news is simply that elsewhere exists, and sometimes it sends messengers. And sometimes we notice. The mathematics of orbital mechanics do not care about poetry. They care about position, velocity, and gravitational force for any object moving through space near a massive body like the Sun. These values determine everything. Plug the numbers into equations refined over centuries, Newton's laws, Kepler's insights, Einstein's corrections, and the result describes a path as inevitable as water flowing downhill. For most objects in the solar system, these calculations yield ellipses. Planets trace ellipses, comets trace ellipses, asteroids trace ellipses. Even the most elongated eccentric ellipses still close upon themselves, returning the object to where it began, binding it forever to the Sun's gravity. The mathematics of 3i/Atlas yield something else. The numbers describe a hyperbola, an open curve that arrives from infinite distance and departs toward infinite distance, never returning. The difference shows up in a single parameter. It only took one number exceeding 1. Orbital eccentricity quantifies how much a path deviates from circular. A perfect circle has eccentricity exactly 0. Earth's orbit has eccentricity 0.017, nearly circular, deviating by less than 2%. Halley's Comet, swinging from beyond Neptune to inside Venus's orbit, has eccentricity 0.967, highly elongated but still bound, still returning every 76 years. At eccentricity exactly 1, the path becomes parabolic, balanced on the knife edge between captive and free. The object arrives from infinity at 0 velocity, curves around the Sun, and departs toward infinity again at 0 velocity, taking infinite time to escape. Any eccentricity greater than 1 breaks free. 3i/Atlas has eccentricity 1.23. The number is not large. The number is enough. This excess eccentricity encodes the object's interstellar velocity, the speed it carries independent of the Sun's gravitational influence. As it falls toward the Sun, gravity accelerates it, adding speed. At perihelion, its closest approach, it will move fastest. But if you subtract the Sun's gravitational contribution, removing the velocity gained by falling inward, what remains is the object's hyperbolic excess velocity. For 3i/Atlas, this value measures approximately 26.3 kilometers per second. This is the speed it had when infinitely far from the Sun, the speed it will have again when infinitely far on the other side. This is its motion through this galaxy, its velocity relative to the local standard of rest, the average motion of stars in the Sun's neighborhood. It only took moving slightly faster than the solar system's orbital dance around the galactic center. The trajectory's shape reveals its origin lies beyond Neptune, beyond the Kuiper belt, beyond the scattered disk where the Sun's influence fades. Backtracking the orbit through time, the path extends outward and outward and outward until it crosses the heliopause, the boundary where solar wind pressure balances interstellar medium pressure, some 18 billion kilometers from the Sun. Before entering this sphere of influence, the object traveled through true interstellar space. Its motion carried it across the galactic disk's plane, threading between stars like a dust mote drifting between searchlights. The precision of backtracking degrades with distance. Small uncertainties in current position and velocity grow exponentially when projected backward across light years. Still, the general direction is clear. 3i/Atlas entered the solar system from the direction of the constellation Lyra, arriving from somewhere in that region of sky, from a past too distant to pinpoint. It only took a few million years of travel. Astronomers compare its trajectory to the trajectories of known stars. Within 200 light-years, thousands of stars occupy space, each moving with its own velocity through the galaxy. By calculating where each star was millions of years ago, and where 3i/Atlas was millions of years ago, They search for coincidences, moments when object and star occupied the same region, suggesting possible origin. The calculations are complicated by galactic rotation, by stellar proper motions, by the three-dimensional dance of stars around the Milky Way's centre. Early results suggest no perfect match. Perhaps the object originated from a star system not yet catalogued. Perhaps it was ejected so long ago that its birth star has moved too far to trace. Perhaps the uncertainties are simply too large. The search continues. It only took becoming homeless to become untraceable. The hyperbolic trajectory also determines how long 3I/Atlas remains observable. As the object approaches perihelion, it brightens both because it draws nearer to Earth and because increased solar heating may trigger outgassing. Creating a faint coma or tail, after perihelion, it dims rapidly. Distance increases. The angle between Earth, Sun, and object becomes less favourable. Reflected sunlight weakens. Within 6 months of discovery, it fades below the detection threshold of all but the largest telescopes. Within a year, it becomes invisible, lost against the background sky. The object does not vanish, it continues on its path, accelerating outward, climbing away from the sun's gravity well, but from Earth, it simply disappears, returning to the category of things we know exist but cannot see. It only took being small and far away. The equations describing its motion are deterministic. Given current position and velocity, the future path is known. No uncertainty remains about the object's fate. It will pass the orbit of Jupiter, then Saturn, then Uranus, then Neptune. It will cross the Kuiper belt, now moving outward where before it moved inward. It will traverse the scattered disk. It will enter the Oort cloud, the vast spherical shell of icy bodies surrounding the solar system, at distances up to 100,000 astronomical units, where the sun's gravity still barely holds sway. It will pass through this shell over thousands of years, unperturbed by its sparse population. And then it will exit, crossing back through the heliopause, returning to interstellar space with nearly the same velocity it carried inward. The sun's gravity bends its path but does not capture it. The visit is temporary. It only took passing too quickly to escape. The terminology used to describe such orbits evolved over centuries. Ancient astronomers saw planets wander against fixed stars and imagined circular perfection. Kepler shattered circles into ellipses. Newton unified terrestrial and celestial mechanics under gravity's single law. Lagrange and Lagrange refined orbital calculations to exquisite precision. By the 20th century, astronomers classified orbits into families circular, elliptical, parabolic, hyperbolic. But until 2017, every orbit observed belonged to the first two categories. Every object detected was bound to the Sun or to a planet. The existence of hyperbolic interstellar objects was theoretical, expected statistically but never confirmed. Oumuamua changed that. 2I/Borisov, a confirmed interstellar comet discovered in 2019, changed it further. 3I/Atlas adds another data point. The family of hyperbolic visitors is no longer theoretical. It only took 4 billion years to start collecting members. There is a philosophical weight to the mathematics. An ellipse implies return, repetition, cyclical time. The object leaves but comes back. Its history and future mirror each other. A hyperbola implies departure, uniqueness, linear time. The object arrives once, leaves once, never returns. Its history and future are asymmetric. For inhabitants of the solar system planets, moons, asteroids, comets, time is measured in orbits. Years are defined by Earth's ellipse. Martian years differ from Jovian years, differ from Mercurial years. But all return. For 3I/Atlas, no such measurement applies. It experiences the solar system as a single event, a brief brightening and warming, then eternal recession. Its time is not cyclical. Its time is an arrow. It only took leaving home to lose the concept of the year. The precision of the calculated orbit improves each night. as more observations accumulate, as more data points constrain the solution, uncertainty shrinks. Early estimates of eccentricity range from 1.19 to 1.27. Current estimates narrow to 1.229 plus or minus 0.004. The perihelion distance closest approach to the Sun refines to 1. 87 astronomical units, placing it between the orbits of Mars and Jupiter, never entering the inner solar system, never warming enough to boil water. The inclination of its path relative to the solar system's plane measures 39 degrees. It crosses our orbital disk at a steep angle, like a needle threading fabric askew. These numbers accumulate slowly. They represent thousands of hours of telescope time, thousands of images processed, thousands of measurements reduced. They are the distillation of human effort applied to the problem of knowing where something is and where it will be. It only took several months of watching to reduce uncertainty to fractions of a percent. The mathematics also reveal what the object is not. It is not a spacecraft. Artificial objects under power show trajectory changes inconsistent with gravity alone. They accelerate, they turn, they do not follow predictable Keplerian paths. 3I/Atlas follows a Keplerian path almost perfectly. Small deviations exist attributed to outgassing forces, to jets of sublimating ice pushing asymmetrically, but these are consistent with natural cometary behavior. No evidence of propulsion appears. No radio signals transmit. No waste heat beyond natural thermal emission radiates. The object is a rock, or ice, or some mixture, obeying physics without intent. Speculation about artificial origin surfaces briefly in popular media, as it does with every unusual astronomical discovery, but the speculation finds no support in data. It only took being strange to invite anthropomorphic interpretation. Light carries information encoded in wavelength. When sunlight reflects off an object's surface, certain wavelengths are absorbed while others bounce back toward Earth. The pattern of absorption creates a spectrum, a rainbow broken into discrete lines and bands, each corresponding to specific molecules and atoms. Spectroscopy reads these patterns like text. It identifies chemical composition without touching, without sampling, without proximity. For 3I/Atlas, spectra reveal a surface bearing the signatures of materials common throughout the universe, but arranged in proportions that differ subtly from solar system bodies. Carbon is present, silicates are present, organic compounds are present, but their ratios, their crystalline structures, their weathering patterns, these carry the fingerprint of formation elsewhere, under a different star's radiation, in a different nebula cloud's chemistry. It only took forming 200 light-years away to develop a different recipe. The visible spectrum shows the object reflects red light more efficiently than blue. This reddening is not rust, not oxidation in the terrestrial sense. It is the slow darkening that occurs when high-energy particles, cosmic rays, solar wind protons, galactic radiation strike organic molecules and break their bonds. The broken fragments recombine into longer carbon chains, into tar-like residues, into materials that absorb shorter wavelengths preferentially. This process occurs throughout the outer solar system. Kuiper belt objects display it. Centaur's asteroids transitioning between the outer planets display it. But those objects reddened under our sun's radiation, within our cosmic ray environment, 3I/Atlas reddened somewhere else, over millions of years, while drifting through interstellar space with a cosmic ray flux determined by nearby supernova remnants, by the local galactic magnetic field, by chance. The color is familiar. The history behind the color is not. It only took aging in darkness under different stars. Infrared spectroscopy detects water ice features. Though faint and diluted, the ice is not pure. It is mixed with dust, with silicate grains, with carbonaceous material. This is expected. Planetary formation models predict that objects condensing in the outer regions of protoplanetary disks, beyond the frost line where water freezes, accumulate as mixtures. Pure ice exists in laboratories. In nature, everything mixes. The water molecules themselves are ordinary two hydrogen atoms, one oxygen atom arranged in the same geometry as water molecules everywhere. But the isotopic ratios, the proportion of deuterium to hydrogen, of oxygen 18 to oxygen 16, these ratios depend on temperature and chemistry during formation. Preliminary measurements suggest deuterium enrichment slightly higher than solar system comets, though within error bars. If confirmed, this would indicate formation in a colder environment, or a different stage of stellar evolution, or simply chance variation in the parent molecular cloud. The difference is small. The difference is real. It only took condensing from a different nebula. Spectral lines from simple molecules appear carbon monoxide, carbon dioxide, perhaps methane. These volatiles freeze at different temperatures. Carbon monoxide sublimates at 25 Kelvin. Carbon dioxide at 80 Kelvin. Water ice remains solid until 150 Kelvin. As 3I/Atlas falls inward and warms, these ices sublimate in sequence, releasing gas that forms a tenuous coma, an atmosphere too thin to breathe, too sparse to trap heat, but dense enough to scatter sunlight and reveal itself to spectroscopy. The composition of the coma matches the composition inferred from surface spectra, confirming that what is seen on the surface extends into the interior. The object is not a thin shell over alien core. It is consistent throughout, or at least down to whatever depth solar heating penetrates. It only took warming from 10 Kelvin to 100 Kelvin to start shedding molecules. The lack of certain spectral features is also informative. No oxygen gas appears, ruling out active photosynthesis. No complex organic signatures emerge, ruling out biological contamination. No industrial pollutants. No artificial isotopes. No phosphine or dimethyl sulfide or other gases associated with life's metabolic byproducts. The object is sterile in the chemical sense, rich in organic molecules, but lacking the particular combinations that biology produces. This is expected. The conditions required for life liquid water, energy gradients, complex chemistry maintained far from equilibrium do not exist on small, cold objects drifting through interstellar space. If life arose in the object's home system, it did not hitchhike on this fragment. If panspermia operates by flinging microbes between stars, this is not a vector. It only took being frozen for millions of years to sterilize any possible contamination. Comparison with Oumuamua's spectrum reveals differences. Oumuamua showed almost no coma, no outgassing, no volatile release even when heated near perihelion. Its spectrum suggested a surface depleted in ices, perhaps stripped by prolonged radiation exposure, perhaps composed of denser rock or metal. Some researchers proposed it was a fragment of a differentiated body, a planetary core or mantle shard ejected during a collision. Others suggested organic tholins, radiation-processed materials coating the surface. 3I/Atlas behaves more like 2I/Borisov, which exhibited clear cometary activity, a visible coma, and spectral features matching solar system comets closely. This diversity is expected. Interstellar objects come from varied environments. Some form near their star, rocky and processed by heat. Others form far out, icy and primitive. They carry no obligation to resemble each other. It only took sampling 3 to find 3 different compositions. The spectrum also records what is absent from our solar system's inventory. Certain crystalline silicate structures appear that form under pressure and temperature conditions rare here. Certain organic molecules show branching patterns that suggest synthesis pathways uncommon in our protoplanetary disk. These differences are subtle, requiring careful calibration and comparison with laboratory experiments. But they persist across multiple observations. They are not instrumental artifacts. They are the chemical fingerprint of a foreign origin. The evidence that different stars produce different nebulae. Different nebulae produce different protoplanetary disks. Different disks produce different objects. The universe is not uniform. Local chemistry varies. It only took crossing interstellar space to deliver a sample. The albedo, the fraction of sunlight reflected rather than absorbed, measures approximately 0.04, making the surface very dark. Darker than charcoal. Darker than asphalt. Nearly as dark as fresh printer toner. This is consistent with carbonaceous material, with organics, with radiation-processed ices. Dark surfaces absorb more heat, warming faster, sublimating volatiles more efficiently. But dark surfaces also cool quickly when the sun recedes. The object's thermal properties depend not just on albedo but on thermal inertia, how quickly heat penetrates and dissipates. High thermal inertia means slow warming and cooling, characteristic of solid rock. Low thermal inertia means rapid temperature swings, characteristic of porous, fluffy material. Observations suggest low thermal inertia. The object is not a solid monolith. It is an aggregate, a rubble pile, loosely bound grains held together by weak gravity and intermolecular forces. It only took being small enough that self-gravity cannot compress. Spectroscopy cannot determine age directly. It measures current state, not history, but the degree of radiation processing, the depth of reddening. The depletion of surface volatiles, these provide constraints. If the object spent 10 million years in interstellar space, cosmic rays would have processed its surface to a certain depth. If it spent 100 million years, the processing would extend deeper. If 1 billion years, deeper still. Calculations suggest an exposure age on the order of tens of millions of years. Though uncertainties are large, this is consistent with ejection from a star system a few hundred light-years away. It is not ancient by geological standards. Earth's oldest rocks are 4.4 billion years old, but it is ancient by the standards of individual objects adrift. It only took a few dozen million years to cross between stars. The mystery is not that the spectrum differs from solar system objects. The mystery is that it differs so little. Carbon, silicon, oxygen, hydrogen, the same elements dominate, the same chemical bonds form, the same molecules condense. Different stars vary in composition. Older stars contain less metal. Younger stars more, but the variation is a few percent, not orders of magnitude. The universe is chemically monotonous. Supernovae distribute heavy elements. Star formation mixes them. Protoplanetary disks fractionate them by temperature and distance. But the starting inventory is similar everywhere. 3I/Atlas could almost pass for a solar system comet. Almost. The differences are there for those who look closely. It only took careful measurement to distinguish foreign from familiar. The crossing between stars is not empty, but it is almost empty. Interstellar space contains, on average, 1 atom per cubic centimetre. This is a vacuum far better than any laboratory can achieve on Earth, where the best vacuum chambers still contain millions of atoms per cubic centimetre. But 1 atom per cubic centimetre, summed over light years, accumulates to mass. A cubic light-year of interstellar medium contains approximately 50,000 kilograms of matter, mostly hydrogen, some helium, traces of heavier elements. This is not nothing. This is the raw material from which stars condense, the reservoir from which planetary systems draw, but it is spread thin. An object travelling through it encounters fewer collisions in 1 million years than a grain of sand encounters in 1 second falling through Earth's atmosphere. The journey is quiet. It only took near vacuum to permit crossing. 3I/Atlas entered this medium millions of years ago when ejected from its birth system. The exact ejection mechanism is uncertain. Perhaps a close encounter with a giant planet, a gravitational slingshot that accelerated it beyond escape velocity. Perhaps perturbations from a passing star stirred the outer edges of its home system's comet cloud, flinging objects into interstellar trajectories. Perhaps a stellar companion many stars form in binary or multiple systems provided the dynamical kick. All three mechanisms are common. Simulations of planetary system evolution routinely produce ejected objects. For every planet that settles into stable orbit, countless smaller bodies are scattered outward, some into distant reservoirs like the Oort cloud, others ejected entirely. The ejection is not catastrophic, it is ordinary. It only took being small and at the wrong place during a gravitational interaction. Once free, the object's velocity relative to its birth star increases with distance. Not because it accelerates, but because escape velocity decreases. Close to a star, gravity holds tight. Far away, gravity weakens. At some distance, the object's kinetic energy exceeds the gravitational binding energy. It is free. It coasts. In the reference frame of its birth star, it moves outward at perhaps 5 or 10 kilometers per second, but stars themselves orbit the galactic center at speeds near 200 kilometers per second, relative to the galaxy. Both the birth star and the ejected object move rapidly, their velocities differing by only a small fraction. Over time, this small difference increases their separation. After 1 million years, the object is light years away. After 10 million years, tens of light years, the birth star fades from bright disk to point of light to invisibility. It only took relative motion through the galaxy. The galactic environment through which it travels is not uniform. The Milky Way's disk contains spiral arms, regions of higher density where gas clouds, young stars, and stellar nurseries concentrate. Between the arms, density falls. The Sun orbits near the inner edge of the Orion Spur, a minor arm branching off the Sagittarius arm. Over millions of years, both the Sun and any interstellar object drift through different galactic neighborhoods. They pass through spiral arms, cross interarm voids, rise above or below the galactic plane. Each region has slightly different cosmic ray flux, different ultraviolet background, different dust density. These variations subtly affect the object's surface chemistry, its radiation exposure, its occasional collisions with dust grains. But the variations are gentle. The galaxy is not a violent place for a small object drifting in interstellar space. It only took moving through slowly changing environments. Radiation becomes the primary interaction. Cosmic rays, high-energy protons, and atomic nuclei, accelerated by supernovae, pulsars, and other energetic events permeate the galaxy. They strike the object constantly, penetrating its surface, breaking chemical bonds, ionizing atoms. Each impact is tiny. Cumulatively, over millions of years, they alter the surface composition, darkening it, polymerizing organic molecules, driving off lighter volatiles. Ultraviolet photons from distant stars contribute similarly. They lack the penetrating power of cosmic rays, but arrive in greater numbers. Together, these processes age the surface, creating a radiation-processed rind distinct from the interior. The interior remains pristine, unchanged since formation, a frozen archive of its birth system's chemistry. The surface becomes a record of its journey. It only took millions of years of exposure. Occasionally, the object encounters interstellar dust grains. These are microscopic particles, typically fractions of a micron across, composed of silicates, carbon, or ice mantles coating mineral cores. At relative velocities of tens of kilometers per second, even micron-sized grains impact with significant energy. They vaporize on contact, creating tiny craters, sputtering atoms off the surface. Over millions of years, countless impacts erode the outermost layers. Grain by grain, this is space weathering at its slowest. On airless bodies in the solar system asteroids, moon space weathering occurs over billions of years. In interstellar space, it occurs over tens of millions. The timescales differ, but the process is identical. Surfaces exposed to space gradually change. It only took patience measured in megayears. The object also passes through molecular clouds vast, cold regions where gas density increases to hundreds or thousands of atoms per cubic centimeter, where temperatures drop to 10 Kelvin, where new stars eventually form. Passage through a molecular cloud lasts thousands of years. During this time, the object experiences increased drag, not enough to slow it noticeably, but enough to ablate atoms from its surface. It also accumulates a thin frost of frozen gases, carbon monoxide. Molecular hydrogen, perhaps complex organic molecules synthesized on dust-grained surfaces. This frost is fragile, microns thick, easily lost when the object exits the cloud and returns to lower density space. But some molecular clouds are dense enough, cold enough, that the frost survives. Layers build up, the surface composition shifts. It only took crossing a molecular cloud to collect new molecules. Gravitational interactions with passing stars are rare but not impossible. In the densest regions of the galactic disk, stellar densities reach 1 star per cubic parsec. A parsec is 3.26 light-years. 1 star per cubic parsec means the nearest star is typically 1 to 2 light-years away. At these distances, gravitational influence is negligible for small objects. But over millions of years, statistically, a close pass occurs. Perhaps the object passes within 1 light-year of a star. Gravity deflects its trajectory slightly. Its direction changes by a degree or two, its speed changes by a kilometer per second or less. The encounter is gentle, nothing like the gravitational slingshots that occur inside planetary systems. But it alters the trajectory. The object that approaches the solar system is not travelling in exactly the direction it left its birth system. It has been nudged by random stellar encounters. It only took millions of years to accumulate small deflections. The journey has no destination. The object does not aim for the solar system. It does not steer. It simply moves according to its velocity vector and the weak gravitational tugs of surrounding mass. The solar system happens to lie along its path. This is coincidence, not purpose. The Milky Way contains hundreds of billions of stars. If ejected objects travel in random directions, and if billions of such objects drift through this galaxy, then occasionally one must pass near any given star. The statistics are simple. The wait time is long, but given enough time, the improbable becomes inevitable. 3I/Atlas is not unique in passing through. It is unique in passing through while humans are watching. It only took waiting 4 billion years for both to happen simultaneously. The crossing is lonely in a way that defies anthropomorphic projection, but invites it anyway. An object without sensors, without awareness, without experience, nevertheless travels in isolation. No sunlight warms it beyond the faint, collective glow of distant stars, a background illumination weaker than moonlight on Earth, insufficient to cast shadows. No planetary system surrounds it. No other objects orbit nearby. It moves through a darkness that is not quite absolute, but nearly so. Through a silence that is not absence of sound. Sound requires medium to propagate. And interstellar space offers almost none but absence of event. Time passes. Distance accumulates. Nothing happens. It only took being ejected to experience the longest, quietest journey imaginable. The heliopause is not a wall, but a boundary where pressures balance. From the sun, solar wind flows outward, a stream of charged particles, mostly protons and electrons, accelerated by the sun's corona to speeds near 400 kilometers per second. This wind carries magnetic fields, energy, and momentum. It expands into space in all directions, pushing against the interstellar medium. But the interstellar medium pushes back. Its pressure is not wind but density, not flow but presence. Where these pressures equalize, The heliopause forms a fluctuating, bubble-like surface marking the edge of the Sun's domain. The distance varies with direction, with solar activity, with local interstellar density. On average, it lies between 15 and 18 billion kilometers from the Sun, roughly 120 astronomical units. Beyond this boundary, the Sun's influence fades to negligible. Within it, the solar system persists. It only took 2 pressures to create a border. 3I/Atlas crosses the heliopause inbound on a trajectory angled 39 degrees from the solar system's plane. The crossing occurs over days, not instantaneously. The heliopause is not sharp. It is a transition region several hundred million kilometers thick where solar wind gradually yields to interstellar plasma. Instruments aboard the Voyager spacecraft, which crossed this boundary decades earlier on their outbound journeys, measured sudden changes in particle density, magnetic field orientation, and cosmic ray flux. 3I/Atlas carries no instruments. It records nothing, but it experiences the transition nonetheless. Cosmic ray flux decreases slightly, the Sun's magnetic field deflects some incoming particles, creating a modest shield. Solar ultraviolet radiation increases. The object begins, very slowly, to warm. It only took entering the heliosphere to begin changing. The warming is minimal at first. At 100 astronomical units, the Sun appears brighter than any star in Earth's night sky, but still far dimmer than seen from Earth. Solar flux at this distance is 10,000 times weaker than at Earth's orbit. The object's surface temperature, which has hovered near 10 Kelvin for millions of years, rises to perhaps 12 Kelvin. This is still far below the freezing point of any known substance except helium. No sublimation occurs, no outgassing begins. The object remains dormant, a frozen aggregate of ice and dust tumbling through space as it has tumbled for ages. But the trend has reversed. For millions of years, it drifted through darkness, cooling toward the cosmic microwave background temperature of 2.7 Kelvin. Now it warms. The change is irreversible within the time frame of its passage. It only took approaching a star. The solar gravitational field begins to dominate the object's trajectory. In interstellar space, gravity is negligible, the nearest stars are light years away, their pull imperceptible. The Milky Way's overall gravitational gradient affects motion only over millions of years. But now, entering the Sun's domain, gravity becomes the primary force. The object accelerates inward, its velocity, measured relative to the Sun, increases. At 100 astronomical units, it moves at roughly 26 kilometers per second. As it falls closer, it will accelerate to 50, then 70, then over 90 kilometers per second at perihelion. The acceleration is continuous, predictable, a consequence of conservation of energy. Gravitational potential energy converts to kinetic energy. The object speeds up. It only took falling into a gravity well. The path curves in interstellar space. The trajectory was nearly straight, minor deflections from stellar encounters aside. It moved in a consistent direction determined by its ejection velocity. Now gravity bends the path into a hyperbola. The object still moves too fast to be captured, but the Sun's mass deflects it significantly. The entry direction and exit direction differ by approximately 90 degrees. The object comes in from one region of sky and leaves toward another. This bending is gravity's signature, the visible proof of mass-warping space-time. Every photon passing the Sun bends slightly. Every comet swinging past bends dramatically. 3I/Atlas bends by an amount determined by its velocity and closest approach distance. It only took mass and proximity. The object's rotation continues unchanged, tumbling on multiple axes. It spins as it has spun for millions of years. The rotation rate, approximately one full rotation every 8 hours, does not slow. Friction requires atmosphere or tidal forces. Interstellar space offered neither. The heliosphere, though denser than interstellar space, is still vacuum. No drag acts. Tidal forces from the Sun exist but are negligible at this distance, relevant only for objects passing far closer than 3I/Atlas will reach. The tumbling persists as the object falls inward, as it accelerates, as its trajectory curves, it spins. The two motions, orbital and rotational, are independent. One does not affect the other. It only took lacking resistance to maintain angular momentum forever. The trajectory brings the object inward through regions previously traversed only by spacecraft and the most distant solar system bodies. At 80 astronomical units, it passes through space once occupied by Voyager 2 decades earlier. At 50 astronomical units, it crosses the average distance of the scattered disk, a region populated by trans-Neptunian objects like Eris and Sedna, leftovers from planetary formation. These bodies orbit the Sun in ellipses. They will return to this region again and again. 3I/Atlas passes through once, never returning. The distinction is absolute. Bound versus unbound. Resident versus visitor. It only took one number eccentricity greater than 1. As it approaches 30 astronomical units, it enters the region where Neptune orbits. Neptune itself is not nearby. The giant planet traces an ellipse that keeps it, on average, this distance from the Sun, but its position at any given moment varies. The object and planet do not encounter each other. Their paths do not intersect. This is fortunate. A close approach to Neptune would gravitationally perturb the object's trajectory, changing its perihelion distance, possibly even capturing it into an ellipse. But the solar system is mostly empty space. The probability of a random object passing close to any planet is small. 3I/Atlas passes through Neptune's orbital zone without interaction. It only took the solar system being mostly void, crossing into the Kuiper belt. The object enters a region more densely populated. Tens of thousands of objects larger than 100 kilometers orbit here, along with countless smaller fragments. This is the solar system's edge, the boundary between planets and interstellar space, a vast reservoir of icy bodies left over from formation. Some Kuiper belt objects are round, large enough that self-gravity compresses them into spheres. Others are irregular, too small for gravity to overcome material strength. 3I/Atlas resembles the latter, a rubble pile, an aggregate, similar in structure to many Kuiper belt objects. But the Kuiper belt objects formed here, condensed from the solar nebula 4.5 billion years ago. They bear the Sun's chemical fingerprint. 3I/Atlas bears a different fingerprint. It only took forming elsewhere to differ subtly. The sunlight strengthens steadily. At 25 astronomical units. Solar flux is 1,600 times weaker than at Earth, but 16 times stronger than at 100 astronomical units. The object's surface temperature rises to 20 Kelvin, then 25. Carbon monoxide ice stable below 25 Kelvin begins sublimating. Molecules escape the surface, evaporating into space. The rate is slow, a few grams per second across the object's entire surface area, but it is non-zero. Outgassing has begun. A tenuous coma forms a cloud of gas surrounding the object, invisible to the naked eye but detectable by sensitive spectrographs. The object is transforming from dormant to active. It only took warming from 10 to 25 Kelvin. The transformation is irreversible during this passage. Molecules that sublimate do not return. They escape the object's weak gravity. Surface escape velocity is less than 1 meter per second and disperse into space. The object loses mass, grain by grain, molecule by molecule. The loss is small. Over the months it spends in the inner solar system, it will shed perhaps a few million kilograms, less than 1% of its total mass. But those kilograms are gone forever, when it exits the solar system and cools again. Returning to 10 Kelvin in interstellar space, it will be fractionally lighter. It will have paid a small toll for passing near a star. It only took warming to begin evaporating. Acceleration toward perihelion is not thrust but falling. The object does not burn fuel, it does not propel itself, it simply descends the sun's gravitational gradient, converting potential energy to kinetic energy according to principles known since Newton. The process is passive, inevitable, mathematical. At 15 astronomical units, it moves at 40 kilometers per second. At 10, 52, at 5, 68. The velocity increases smoothly, continuously, predictably. Orbital mechanics textbooks contain the equations. Plug in mass of the Sun, distance from the Sun, and the hyperbolic excess velocity. The output is speed as a function of distance. The curve is steep near perihelion, shallow far away. It only took falling closer to gain speed. The trajectory carries the object inward through the orbits of outer planets. At 10 astronomical units, it crosses Saturn's average distance from the Sun. Saturn itself is elsewhere in its orbit, tens of degrees away along the ecliptic. No encounter occurs. The object continues unperturbed. At 5 astronomical units, it passes through Jupiter's orbital zone. Again, no encounter. Jupiter's gravity is immense, 300 times Earth's mass, and could dramatically alter the object's path if it passed nearby. But nearby, in astronomical terms, means within a few million kilometers. The object's trajectory misses Jupiter by hundreds of millions of kilometers. The giant planet's influence is negligible. It only took the solar system being vast. Light from the Sun intensifies. At 5 astronomical units, solar flux is still 25 times weaker than at Earth, but enough to drive significant sublimation. Carbon dioxide ice, stable below 80 Kelvin, begins to vaporize. The coma grows thicker, more extended. Dust grains embedded in the ice, released as the ice sublimates, form a faint tail. The tail is not the bright, sweeping structure of a great comet. It is subtle, detectable only by telescopes. The object is small, its activity is modest, but it is active. Gas and dust stream away continuously, pushed by solar radiation pressure and solar wind. The tail points away from the Sun, always away, regardless of the object's direction of motion. It only took radiation pressure to orient the tail. The object crosses the asteroid belt, that diffuse ring of rocky bodies orbiting between Mars and Jupiter. Despite popular imagination, the asteroid belt is not dense. Spacecraft pass through it routinely without collision. Asteroids are separated by millions of kilometers. The total mass of all asteroids combined is less than the Moon's mass. 3 I/Atlas threads through this sparse population without incident. The asteroids do not notice. The object does not notice. Gravitational interactions at these distances and masses are insignificant. It only took mostly empty space. At 3 astronomical units, the object enters the realm where sunlight begins to dominate over reflected starlight. For billions of years, the brightest light falling on its surface was the collective glow of the Milky Way, a faint background insufficient to cast shadows or warm surfaces. Now, the Sun is a distinct disk, small but brilliant, casting clear shadows across the object's irregular terrain. Craters, ridges, fractures, whatever topography exists on its surface emerge from uniform illumination into chiaroscuro. One side faces the Sun and warms, the other side faces space and remains cold. Temperature gradients develop, thermal stress fractures propagate, the object creaks and groans in silence. Adjusting to the new regime, it only took direct sunlight, water ice, stable below 150 Kelvin, remains solid but begins to soften. At the subsolar point, the location on the surface where the Sun hangs directly overhead, temperatures reach 120 Kelvin. This is still far below water's melting point. Water at 120 Kelvin is as hard as granite, but vapor pressure increases exponentially with temperature. Even solid ice releases molecules into the vacuum. Sublimation rate. which was negligible in interstellar space, now reaches kilograms per second. The coma thickens further. Spectroscopy from Earth detects water vapor mixed with carbon monoxide and carbon dioxide. The object's composition reveals itself. It only took warming past 100 Kelvin. The tumbling rotation creates uneven heating. As the object spins, different faces turn toward the sun in sequence. Each face warms during its daylight hours and cools during its night. But rotation is fast 8 hours for one complete cycle, and thermal conductivity is poor. Heat penetrates only millimeters into the surface during each rotation. The result is a surface with wildly varying temperatures 120 Kelvin at the subsolar point, 50 Kelvin on the night side. Interior temperatures lag far behind, a meter beneath the surface. The material remains at 10 Kelvin, unchanged from interstellar space. The object is thermally stratified. It only took poor conductivity. Outgassing creates non-gravitational forces. As gas escapes the surface, it carries momentum. The escaping molecules push against the object, producing thrust. For a large, massive body, this thrust is negligible. For a small, low-mass object like 3I/Atlas, it is measurable. The trajectory deviates slightly from a purely gravitational path. The deviation is small, a few kilometers over the entire passage through the solar system, but detectable. Astronomers measure it by tracking the object's position over weeks and comparing to predicted positions. The discrepancy indicates outgassing. The direction and magnitude of the discrepancy reveal which side of the object is most active. It only took sublimation to become a rocket. At 2 astronomical units, the object crosses Mars's orbital distance. Mars is not nearby. No encounter occurs, but the object now occupies the same region of space as the inner planets Earth, Venus, Mercury, Mars. It has entered the Sun's inner system, the warm zone where rocky planets formed, where temperatures are high enough to vaporize ices and concentrate metals. For solar system natives, this is home. For 3I/Atlas, it is a brief visit. Its perihelion lies just ahead, at 1.87 astronomical units, a distance placing it between Mars and Earth but closer to Mars. It will not approach Earth. It will not pass near Venus. It will reach its closest point to the Sun and immediately begin receding. It only took hyperbolic trajectory to ensure brevity. Brightness peaks as distance from Earth decreases and solar heating increases. Ground-based telescopes track it nightly. Space telescopes dedicate observation time. Spectra accumulate. Light curves refine. The data stream is rich, unprecedented for an interstellar object. Oumuamua faded quickly, observed for only weeks before becoming too faint. 3I/Atlas remains observable for months. Its trajectory is more favorable. Its activity is stronger. Astronomers have time to measure carefully, to compare instruments, to refine models. They gather data that will be analyzed for years. It only took being discovered early in its approach. The Sun's tidal forces remain weak. Tidal forces arise from gravitational gradients, the difference in gravitational pull across an extended object. Earth's moon raises tides on Earth because gravity is stronger on the side of Earth facing the moon than on the far side. The difference stresses Earth's oceans and crust. For 3I/Atlas, passing at 1.87 astronomical units, the Sun's tidal forces are minuscule. Across the object's 400-meter diameter, the gravitational gradient is negligible. The object feels the Sun's gravity as nearly uniform. No tidal disruption occurs. No fracturing from tidal stress. It remains intact. It only took not passing too close. Perihelion approaches. The object's velocity, measured relative to the Sun, reaches 92 kilometers per second. This is the fastest it will ever move during its passage. After perihelion, it will slow as it climbs outward, converting kinetic energy back to potential energy, rising out of the Sun's gravity well. but for now, it races inward at speeds that dwarf human experience. 92 kilometers per second is 330,000 kilometers per hour. It is fast enough to circle Earth's equator in 2 minutes. It is fast enough to cross the distance from Earth to Moon in an hour. But space is vast. Even at this speed, the object takes months to traverse the inner solar system. It only took gravitational acceleration to reach relativistic speeds well. Not relativistic, but impressively fast by terrestrial standards. The warming of alien ice is a phase transition without melting. Water ice, carbon dioxide ice, carbon monoxide ice, these compounds exist in multiple crystalline structures depending on temperature and pressure. At 10 Kelvin, water ice is amorphous, its molecules frozen in disordered arrangements. At 100 Kelvin, it transitions to cubic crystalline form. At 150 Kelvin, it becomes hexagonal crystalline ice, the familiar structure of snowflakes and frost. Each transition releases stored energy, adjusts density, changes optical properties. 3I/Atlas, warming from 10 Kelvin to 150 Kelvin over months, passes through these transitions sequentially. The ice restructures grain by grain, bonds break and reform. The material creaks under internal stress. It only took warming to rearrange molecular geometry. Sublimation rate increases exponentially with temperature. At 50 Kelvin, carbon monoxide ice sublimates slowly, releasing perhaps 1 kilogram per second across the object's surface. At 100 Kelvin, sublimation reaches 10 kilograms per second. At 150 Kelvin, water ice joins the outgassing, adding another 10 kilograms per second. The total mass loss rate remains tiny compared to the object's total mass estimated at several billion kilograms, but the cumulative loss over months becomes significant. By perihelion, the object will have shed millions of kilograms, carving shallow pits where sublimation was most vigorous, exposing fresh material beneath the radiation-darkened surface. The process is erosion without weather. It only took solar heating. The escaping gas carries dust. Ice is not pure. It contains embedded grains, silicates, carbonaceous particles, organic compounds mixed during formation. As ice sublimates, these grains are released. Small grains, micron-sized, are swept away by gas drag. Larger grains, millimeter-sized, fall back to the surface under the object's weak gravity. The result is a sorting mechanism. Fine dust escapes, coarse dust accumulates. Over time, this process creates a lag deposit, a layer of non-volatile material blanketing the surface, insulating the ice beneath, slowing further sublimation. Many comets develop such layers. 3I/Atlas, warmed only once by this sun, develops a partial lag deposit where sublimation is most intense. It only took 1 perihelion passage to alter surface texture. The coma extends outward, growing with distance from the object's nucleus. Gas molecules, once released, travel ballistically. At the nucleus surface, gas density is high enough for collisions. Molecules bump into each other, thermalize, expand collectively. Farther out, collisions become rare. Molecules travel in straight lines, spreading into space. The coma's boundary is not sharp. It fades gradually, density decreasing with distance according to inverse square law. At 1,000 kilometers from the nucleus, the coma is still detectable. At 10,000 kilometers, it becomes tenuous. At 100,000 kilometers, it merges with the solar wind and interplanetary medium. The object's influence extends far beyond its solid body. It only took outgassing to create an extended atmosphere. Sunlight interacts with the coma's molecules. Ultraviolet photons, energetic and abundant near the sun, strike water molecules and dissociate them into hydrogen and oxygen. They strike carbon dioxide and break it into carbon monoxide and oxygen. These fragments, called radicals, are chemically reactive, unstable, short-lived. They glow faintly as they de-excite, emitting photons at specific wavelengths. Hydroxyl radicals oxygen bonded to hydrogen emit in the ultraviolet. Cyanogen radicals emit in the visible blue. These emissions create a faint fluorescence, a glow surrounding the nucleus, detectable by spectroscopy. The object becomes briefly luminous, not from its own heat but from solar-driven chemistry. It only took ultraviolet irradiation. The tail develops structure. Dust grains, pushed by solar radiation pressure, form a broad, curved tail. Gas molecules, ionized by solar ultraviolet and swept by solar wind, form a straighter, narrower tail pointing directly away from the sun. The two tails are distinct, visible in images as separate features. The dust tail is yellowish, reflecting sunlight. The gas tail is bluish, fluorescing. Together they create the classic cometary appearance. Though faint compared to great comets like Hale-Bopp or Hyakutake, 3I/Atlas is not spectacular. It is observable. It only took modest activity to develop dual tails. Thermal inertia measurements reveal the object's interior structure. Thermal inertia quantifies how quickly a material responds to heating or cooling. Solid rock has high thermal inertia. It warms slowly, cools slowly, retains heat. Porous. Fluffy material has low thermal inertia. It warms quickly, cools quickly, stores little heat. By measuring how the object's surface temperature changes with solar distance and rotation phase, astronomers infer thermal properties. Results indicate low thermal inertia, consistent with a porous structure. With void space between grains, with material resembling loosely packed snow more than solid rock, the object is not a monolith. It is an aggregate held together by weak self-gravity and molecular forces. It only took being small to remain uncompressed. Porosity affects sublimation in subtle ways. Gas released from subsurface ice must percolate through overlying layers to escape. If the material is porous, gas escapes easily. If layers are compacted or sealed by lag deposits, gas pressure builds. Eventually, pressure exceeds material strength. The surface fractures. Gas bursts outward in a jet. Such jets are observed on solar system comets, discrete plumes erupting from specific locations, sometimes rotating with the nucleus, sometimes shifting position. Images of 3I/Atlas lack sufficient resolution to detect individual jets, but brightness variations suggest localized activity. Certain regions of the surface outgas more vigorously than others. The object is not uniformly active. It only took structural heterogeneity. Isotopic ratios measured in the coma provide clues to formation temperature. Deuterium-hydrogen with an extra neutron forms in cold environments. The colder the environment, the higher the deuterium to hydrogen ratio in water ice. Solar system comets show a range of ratios, suggesting formation at varying distances from the Sun. 3I/Atlas shows a ratio slightly elevated compared to Earth's oceans, comparable to some solar system comets, but with uncertainties large enough to prevent definitive conclusions. The ratio is consistent with formation beyond the frost line in a protoplanetary disk. It is consistent with formation in a cold molecular cloud before disk formation. It is consistent with multiple scenarios. The data are suggestive, not definitive. It only took limited spectral resolution to leave ambiguity. The surface erodes unevenly. Regions facing the Sun during perihelion sublimate vigorously, losing meters of material, regions perpetually in shadow, protected by the object's own topography, remain unchanged. Craters, if they exist, may deepen or shallow depending on orientation. Cliffs may retreat, boulders may tumble as supporting ice sublimates. The object emerges from perihelion subtly reshaped, its topography modified by erosion at rates that would require millions of years in interstellar space but occur here over months. Solar heating is efficient. It only took proximity to a star. By perihelion, the object's appearance is transformed. What entered the solar system as a dark, dormant iceberg now sports a coma thousands of kilometers across. twin tails extending millions of kilometers, a nucleus venting gas and dust. It has awakened. But the awakening is temporary, reversible. After perihelion, as it recedes from the sun, temperatures will drop, sublimation will slow, then cease, the coma will dissipate, the tails will fade, the object will return to dormancy, carrying with it the scars of passage, a slightly lower mass, a slightly altered surface, a slightly different shape but otherwise unchanged in essence. It only took one star to briefly animate. Perihelion is not an event but a moment, the instant when distance to the sun reaches minimum. For 3I/Atlas, this occurs at 1.87 astronomical units, 280 million kilometers from the sun's center. The distance places it between the orbits of Mars and Earth, closer to Mars by 70 million kilometers. At this distance, solar flux is 35% of Earth's value. Sunlight is weaker than at Earth, but far stronger than anywhere the object has experienced in millions of years. The subsolar point on its surface reaches 160 Kelvin. Water ice sublimates actively. Carbon dioxide ice has already vaporized. The object is at peak activity, shedding mass at its maximum rate, glowing faintly in spectroscopic emissions, surrounded by the thickest coma it will develop. It only took falling this close. Velocity peaks simultaneously. At perihelion, the object moves at 92.4 kilometers per second relative to the Sun. This is its maximum speed, the point where kinetic energy is highest and potential energy lowest. The velocity vector is perpendicular to the radius vector. The object moves tangentially, not inward or outward, crossing through the perihelion point at right angles to the Sun's direction. This perpendicular configuration is geometrically necessary. At any other angle, the object would be either approaching or receding, meaning perihelion had not yet occurred or had already passed. The mathematics dictate geometry. It only took conservation of energy and angular momentum. The Sun's gravity at this distance exerts its strongest pull, gravitational acceleration proportional to inverse square of distance. Measures approximately 1 millimeter per second squared. This is tiny compared to Earth's surface gravity, 9.8 meters per second squared, but significant across the object's trajectory. Over the hours spent near perihelion, gravity curves the path noticeably. The hyperbola bends most sharply here. If the trajectory were plotted on paper, this would be the region of tightest curvature. The moment when the object changes direction most rapidly, inbound velocity differs from outbound velocity by roughly 90 degrees. The Sun deflects without capturing. It only took mass warping spacetime. Tidal forces remain negligible but reach their maximum. The gravitational gradient across the object's 400-meter diameter creates differential forces measuring fractions of a micronewton per kilogram. This is far below the object's material strength. Rock, ice, even loosely bound aggregates can withstand stresses millions of times larger. Comets have passed far closer to the Sun without disrupting. Comet Lovejoy grazed the Sun's corona and survived. 3I/Atlas, passing at a comfortable distance. Experiences no tidal threat. Its structural integrity is unchallenged. It remains intact, tumbling as it has tumbled, unperturbed by stress. It only took not passing within the Roche limit. Rotation continues unchanged. The object spins with a period of 8 hours, tumbling on multiple axes. This rotation predates solar system entry by millions of years. Perihelion passage does not alter it. There is no mechanism to slow or speed the spin. Tidal forces are too weak. Outgassing, which can create torques, is symmetric enough to produce minimal net angular momentum change. The tumbling persists, frame invariant, independent of orbital position. The same face that pointed sunward in interstellar space points sunward now, except shifted by the continuous rotation. There is no synchronous locking, no tidal braking, no dynamical evolution. It only took lacking strong external torques, outgassing reaches maximum intensity. Perhaps 20 kilograms per second escape the surface a mix of water vapor, carbon dioxide, carbon monoxide, with entrained dust grains. This rate is modest by cometry standards. Comet Halley, at perihelion, ejects thousands of kilograms per second. But Halley is larger, more active, closer to the Sun. 3I/Atlas is small and distant. Its activity, though peaked, remains subdued. The coma extends perhaps 5,000 kilometers from the nucleus. The tail stretches millions of kilometers but remains faint. Observers describe it as diffuse, subtle, requiring telescopic aid. It is not visible to the naked eye. It only took being small and distant. Non-gravitational acceleration from outgassing reaches its maximum magnitude. The thrust generated by escaping gas pushes the object slightly off its gravitational trajectory. The deviation accumulates to several kilometers over the perihelion passage. Astronomers measure this by comparing observed positions to predictions. The discrepancy reveals outgassing distribution. If gas escapes primarily from the sunward side, it pushes the object outward, increasing orbital energy slightly. If gas escapes from the night side delayed by thermal lag or subsurface heating, it pushes inward. The observed deviation indicates sunward dominant outgassing with asymmetries suggesting active regions near the equator. The object's trajectory is subtly altered. It only took rocket forces measured in micronewtons. Dust grains released at perihelion follow their own trajectories. Small grains, micron-sized, are swept outward by radiation pressure faster than the object's orbital velocity. They form the dust tail spreading into space, each grain on its own heliocentric orbit. Larger grains, millimeter to centimeter sized, receive less radiation pressure and remain closer to the object's orbital path. Over time, these grains disperse along the orbit, forming a debris trail. If Earth's orbit intersected this trail, the grains would burn up in Earth's atmosphere as meteors. But Earth's orbit does not intersect. The grains remain in space, invisible, undetectable except by chance spacecraft encounter. They are the object's legacy. It only took shedding dust. The Sun, seen from the object's surface, is a disk 9 times smaller than seen from Earth. Its angular diameter measures 3 arc minutes 1/10 of a degree. This is small but resolvable, a distinct disk rather than a point. Solar features sunspots, faculae. Prominences are invisible at this distance and resolution. The Sun is simply a brilliant white disk, flooding the daylight side with light, casting sharp shadows, heating surfaces to temperatures that drive sublimation. For an observer standing on the object hypothetically, impossibly the Sun would dominate the sky despite its small size. Its brightness would overwhelm all stars, rendering them invisible. The Milky Way's band, visible from interstellar space, would vanish in solar glare. It only took one star nearby to erase the galaxy. The moment of perihelion lasts no longer than any other moment. It is not stretched, not emphasized, not marked by physical discontinuity. The object reaches minimum distance and immediately begins receding. There is no pause, no dwelling. The trajectory is smooth, continuous, differentiable. Velocity transitions from radially neutral with tangential component to radially outward with tangential component without discontinuity. Calculus describes it perfectly. The first derivative of distance with respect to time passes through zero. The second derivative remains positive. Distance is minimized, velocity is maximized, acceleration points sunward but decreasing. It only took passing the turning point. After perihelion, recession begins immediately. The object climbs out of the Sun's gravity well, converting kinetic energy back to potential energy. Slowing as it ascends, the slowing is gradual, imperceptible over minutes, measurable over days. Velocity at perihelion plus 1 hour is still above 90 kilometers per second. Velocity 1 day later has dropped to 85. The curve is smooth, predictable. The time reverse of the inbound acceleration. Every event that occurred during approach will occur again during departure. Reversed? Warming will become cooling. Brightening will become dimming. Activity will wane. The object will return to dormancy. It only took starting to leave. Earth-based observers note the perihelion passage with routine precision. Telescopes track the object across the sky, measuring position every few hours. The data confirm predicted positions within error bars. No surprises emerge. The object behaves as expected, following gravitational mechanics with minor outgassing perturbations. Models match observations. The passage is scientifically productive, but not anomalous. It adds data to the sparse catalogue of interstellar objects. It refines understanding of cometary activity. It provides a comparison point for future detections. But it does not revolutionize understanding. It confirms what was expected. It only took one more example. Asymmetric forces arise from asymmetric outgassing. The object's surface is not uniform. Some regions contain more ice, others more dust. Some areas are smooth, others fractured. As sunlight heats the surface, outgassing occurs preferentially from ice-rich regions. These regions act as jets, venting gas more vigorously than their surroundings. The escaping gas carries momentum, action and reaction. The object experiences thrust opposing the gas flow. If jets are symmetrically distributed, thrusts cancel, but jets are not symmetrically distributed. The object's shape is irregular, its composition heterogeneous, its rotation complex. Jets fire from random orientations at different times with varying intensity. The net thrust is non-zero. It only took being irregularly shaped. The thrust creates acceleration measured in fractions of a millimeter per second squared. This is tiny compared to solar gravity, but cumulative over time. Hours of continuous outgassing produce velocity changes of meters per second. Days produce tens of meters per second. These velocity changes alter the trajectory. The object deviates from a purely gravitational path by kilometers, then tens of kilometers. Astronomers measure the deviation by tracking position against star fields. Night after night, they photograph the object and calculate its coordinates. Predicted positions assume gravity only. Observed positions show systematic offset. The offset's direction and magnitude reveal outgassing patterns. It only took careful measurement to detect thrust. The tumbling complicates analysis. The object rotates every 8 hours, presenting different faces to the Sun in sequence. Each face has different outgassing properties. As rotation carries an active region into sunlight, a jet turns on. As rotation carries it into shadow, the jet weakens. The on-off cycle repeats with each rotation. Thrust direction changes cyclically. Over one rotation period, thrusts partially cancel, but not completely. Asymmetries in jet distribution, in thermal lag, in surface properties, create net residual thrust that does not average to zero. The object accelerates erratically, its trajectory perturbed by rotation-dependent forces. It only took tumbling to create complexity. Light curves, graphs of brightness versus time reveal the rotation through periodic variations. As the object tumbles, different surface areas reflect sunlight toward Earth. If the object were spherical and uniformly reflective, brightness would remain constant. But the object is elongated and variably reflective. Dark regions rotate into view, brightness drops. Bright regions rotate into view, brightness rises. The pattern repeats every 8 hours. By analysing light curve shape, astronomers infer rough geometry likely elongated 3:1, possibly irregular, definitely not spherical. Detailed shape reconstruction requires more data than available. The light curve provides hints, not certainty. It only took watching brightness oscillate. The tumbling is non-principal axis rotation. Most rotating objects spin around their principal axis, the axis of maximum moment of inertia. The stable configuration. A football thrown with a tight spiral spins around its long axis. Stable, but if thrown poorly, it wobbles, tumbling end over end while also spinning. This is non-principal axis rotation. Dynamically complex, energy dissipative in the presence of internal friction. 3I/Atlas tumbles this way. Its rotation state is not stable. Over time, tens of thousands of years internal friction from stress and relaxation would damp the tumbling into principal axis rotation. But tens of thousands of years have not passed. The object retains its complex rotation, established millions of years ago, not yet damped. It only took lacking enough time to settle. Specular reflections create brightness spikes. If the surface contains flat, smooth regions, ice facets, exposed bedrock, fresh fracture surfaces, these can act as mirrors, briefly reflecting sunlight directly toward Earth. When rotation aligns such a facet perpendicular to the Sun object Earth plane, brightness spikes. The spike lasts minutes. The time required for rotation to misalign the facet. Several such spikes appear in the light curve, suggesting multiple reflective surfaces. Their timing and intensity constrain surface properties. The surface is not entirely rough. It contains patches smooth enough to reflect specularly. It only took having some flat spots. Polarimetry measures light polarization, revealing information about surface texture. Smooth surfaces produce highly polarized reflected light. Rough surfaces depolarize light, scattering it in random directions. Observations show low polarization, indicating rough surface texture at scales comparable to light wavelength microns to millimeters. This is consistent with a regolith-like surface, covered in dust and small grains, lacking large smooth areas. The occasional specular spikes must come from small, localized facets embedded in an otherwise rough matrix. The surface is complex, textured, varied. It only took measuring polarization angles. Thermal modeling attempts to reconcile observations with theory. The model assumes a shape, perhaps a triaxial ellipsoid, assigns thermal properties like albedo and thermal inertia, simulates solar heating and sublimation, and predicts brightness and temperature as functions of time. The predictions are compared to observations. Discrepancies suggest model adjustments. Dozens of parameters are tweaked iteratively until model and observation align. The final model is not unique. Multiple parameter sets can fit the data, but it is constrained. It brackets possibilities. The object's properties lie within ranges defined by best fit models. It only took computational iteration. Rotation period measurement improves with time. Early estimates range from 7 to 9 hours. Additional observations narrow the range. Current best estimate 8.23 hours plus or minus 0.15 hours. This precision allows prediction of brightness at future times, aiding observation planning. Telescopes can be scheduled to observe during brightness maxima, improving signal to noise. The rotation is remarkably constant. No evidence of spin-up or spin-down appears. The object rotates as a rigid body, not a fluid or loosely bound rubble pile. Its structure, though porous, has sufficient cohesion to rotate uniformly. It only took internal strength. The tumbling light pattern becomes hypnotic over repeated observations. Brightness rises and falls, peaks and troughs, with metronomic regularity. Each 8-hour cycle resembles the previous. The periodicity is comforting, predictable, mathematical. But underlying the periodicity is chaos. The object's actual rotation state is chaotic in the technical sense. Sensitive to initial conditions, never exactly repeating. Over thousands of rotations, tiny differences accumulate. The light curve drifts slowly, but over the observation window of months, the drift is negligible. The pattern repeats with clock-like precision. It only took observing for short enough time. The object reflects light from a star not its own. For millions of years, it drifted under the collective light of the galaxy, hundreds of billions of stars contributing photons, none dominant. Now it reflects light from one star, the Sun, overwhelmingly brighter than all others combined. The photons striking its surface left the Sun 8 minutes ago. They travelled outward at light speed, spread in all directions, filling space with electromagnetic radiation. A tiny fraction struck the object. A tinier fraction reflected toward Earth. Those photons, carrying information about the object's surface properties, entered telescopes, excited detector pixels, became data. The light reveals it only took photons bouncing off alien ice. Departure through planetary orbits is the mirror of entry, but not identical. The object recedes from perihelion with velocity gradually decreasing, climbing out of the Sun's gravity well as it climbed in. But along a different path. The hyperbola's two branches are symmetric in shape, but not in space. The inbound path arrived from one direction. The outbound path departs towards another, deflected by approximately 90 degrees. The object will not retrace its entry route. It will exit the solar system in a different direction than it entered, the Sun's gravity having bent its trajectory permanently. It only took one close pass to redirect. At 2 astronomical units outbound, 10 days after perihelion, the object's velocity has dropped to 84 kilometers per second. It crosses the orbital distance of Mars, moving outward. Mars itself, as during entry, is elsewhere. No encounter occurs. The object continues unperturbed, still active but waning. Surface temperature at the subsolar point has dropped to 140 Kelvin. Water ice sublimation continues but slows. Carbon dioxide, already depleted near the surface, vents weakly. The coma begins to shrink. Outgassing rate falls from 20 kilograms per second to 15, then 10. The object is shutting down. It only took moving farther from heat. The dust tail, pushed outward by radiation pressure, now points back toward the Sun. During approach, the tail pointed away from the Sun but trailed behind the object. During departure, it points away from the Sun but extends ahead of the object. This reversal is characteristic of cometary tails. They do not stream behind like hair in the wind. They point away from the Sun regardless of motion direction. Radiation pressure and solar wind dictate orientation, not velocity. The tail precedes the departing object, a luminous banner marking its path. It only took solar photons pushing dust grains. At 3 astronomical units, 1 month post-perihelion, the coma has thinned noticeably. Gas production drops below 5 kilograms per second. The dust tail fades, individual grains dispersing into separate heliocentric orbits. Spectroscopic detection of water vapor weakens. Only carbon monoxide remains easily detectable. Still sublimating from deeper layers where solar heat penetrated during perihelion, the object transitions from active comet to dormant body, the transformation gradual but inexorable. Cooling follows heating with thermal lag measured in weeks. It only took distance to quiet activity. The asteroid belt is crossed outbound. Again, no collisions. The belt's population, though numerous, occupies vast volumes. Random encounters are improbable over human timescales. Over billions of years, statistically, every orbit intersects every other orbit eventually. But billions of years have not passed for this trajectory. The object threads through empty space between asteroids, gravity pulling it outward and outward, velocity dropping but never reversing. It will not turn around. It will not orbit. It only took hyperbolic excess velocity. At 5 astronomical units, crossing Jupiter's orbital distance outbound, velocity is decreased to 68 kilometers per second. This matches the inbound velocity at the same distance. The symmetry is exact, a consequence of energy conservation. Kinetic plus potential energy equals constant. At equal distances, kinetic energies are equal, velocities are equal, but directions differ. Inbound velocity pointed roughly sunward. Outbound velocity points away, perpendicular to the inbound vector. The energy is conserved. The trajectory is transformed. It only took gravity conserving energy while changing direction. Surface temperature continues dropping at 5 astronomical units. Subsolar temperature reaches 90 Kelvin. Water ice no longer sublimates. Its vapor pressure falls below detection thresholds. Only carbon monoxide remains marginally active. And weakly, the coma dissipates entirely. Within weeks, spectroscopy can no longer detect gas emission. The object returns to appearing as a point of reflected light, indistinguishable from an asteroid except for its trajectory. The cometary phase has ended. It lasted perhaps 4 months, from initial activity at 20 astronomical units inbound to cessation at 6 astronomical units outbound. 4 months of activity bracketed by millions of years of dormancy. It only took brief warming. Brightness fades rapidly with increasing distance. Brightness depends on both distance from Sun and distance from Earth. As the object recedes, both distances increase. Reflected sunlight decreases as inverse square of solar distance. Apparent brightness decreases as inverse square of Earth distance. Combined, brightness falls as 4th power of distance approximately. At 10 astronomical units, the object is 16 times fainter than at perihelion. At 15, 81 times fainter. Telescopes lose ability to track it. Exposure times lengthen. Signal-to-noise ratios deteriorate. Observations become sporadic, then cease. It only took distance and geometry. At 10 astronomical units, crossing Saturn's orbital zone outbound, the object's surface temperature has fallen to 40 Kelvin. All sublimation has ceased. The surface refreezes. Though refreezes is imprecise water, ice never melted, never liquefied. It transitioned from sublimating solid to stable solid. The crust of lag deposit remains, a thin armour of dust and non-volatile grains protecting the ice beneath. Beneath this crust, the interior cools slowly. Heat deposited during perihelion diffuses inward, millimetre by millimetre, over months and years. Eventually thermal equilibrium will restore. The interior will return to 10 Kelvin, but not yet. It only took meters of insulation. The tail has vanished entirely. Dust grains, no longer replenished by outgassing, dispersed into independent orbits. Each grain now orbits the Sun on its own trajectory, perturbed by radiation pressure, by solar wind, by eventual collisions with other grains. The tail existed for months. The grains will orbit for millions of years until collisions grind them to finer dust, until they spiral into the Sun under Poynting Robertson drag, until they're swept up by planets or ejected by gravitational interactions. They are the object's scattered legacy, unbound from their parent, drifting in solar orbits that will never bring them together again. It only took outgassing to disperse them. Non-gravitational acceleration ceases. Without outgassing, without thrust, the object's trajectory becomes purely gravitational. Its path through space is now determined solely by its current position and velocity, and the Sun's mass. The equations simplify. Perturbations from planets are calculable, predictable. Minimal unless a close encounter occurs. No close encounter is predicted. The object will coast outward on a clean hyperbola. A textbook example of two-body dynamics. The complexity of activity, of jets, of tumbling-induced thrust variations all fade into irrelevance. The trajectory is now clean. It only took cessation of sublimation. Observations end approximately 6 months post-discovery, 4 months post-perihelion. When the object fades below magnitude 24, the limit of even large professional telescopes for faint, moving targets, final position and velocity are recorded. The orbital elements are refined to their ultimate precision. Uncertainty in future position grows with time but remains small for decades. In 50 years, the object's position will be known to within a few million kilometers. In 500 years, within tens of millions. In 5,000 years, within hundreds of millions. Eventually, uncertainty exceeds the solar system's size and predictions have become meaningless. But for human timescales, the trajectory is known. It only took 6 months of observation. The object continues outward, now invisible, now unobserved, but tracked mathematically. Computers integrate its orbit forward in time at 20 astronomical units. Predicted date such and such at 30. Predicted date such and such. Predictions extend centuries, millennia. They're reliable within growing error bars. The object becomes a number in a database, a row in a table of orbital elements, a footnote in the catalogue of interstellar visitors. It recedes from human awareness as it recedes from the sun. It only took fading below detection threshold. Telescopes watching it leave operate from 2 locations, ground and space. Ground-based observatories scattered across Earth in deserts, on mountains, in remote locations chosen for dark skies and clear weather track the object nightly when weather permits. Each telescope captures images, measures positions, records brightness. The images are digital, stored as arrays of numbers representing photon counts per pixel. Software pipelines process the data automatically, subtracting backgrounds, correcting for instrumental effects, extracting source positions to sub-pixel precision. The object appears as a faint smudge, sometimes elongated by the coma, sometimes point-like. It moves against the background stars, its motion measurable over minutes. It only took digital sensors to automate tracking. Space-based telescopes observe without atmospheric interference. Earth's atmosphere distorts light, blurs images, absorbs certain wavelengths. Space telescopes orbit above the atmosphere, capturing sharper images, accessing ultraviolet and infrared wavelengths blocked from ground. Hubble Space Telescope observes the object in visible and ultraviolet light. Spitzer, before its retirement, captured infrared images. James Webb Space Telescope allocates observation time, imaging in near-infrared, detecting thermal emission from the warming then cooling nucleus. Each telescope contributes unique data. Each wavelength reveals different properties. Combined, they construct a multispectral portrait. It only took multiple instruments. Spectroscopy from both ground and space captures the object's chemical fingerprint. Spectrographs split reflected sunlight into constituent wavelengths, revealing absorption and emission lines. Each line corresponds to a specific molecule or atom. Water vapor shows its signature. Carbon monoxide shows its signature. Hydroxyl radicals emit at characteristic wavelengths. By measuring line strengths, astronomers calculate gas production rates, isotopic ratios, temperature estimates. Spectra are collected nightly when possible, building time series data showing how composition changes with solar distance. Activity rises toward perihelion, falls afterward. The spectral evolution mirrors the thermal evolution. It only took dispersing light into spectra. Radio telescopes listen for emissions at longer wavelengths. Radio observations can detect molecules like carbon monoxide and formaldehyde through rotational transitions. These transitions occur at millimeter and centimeter wavelengths, far beyond optical range. Radio telescopes' large dishes scattered across continents, sometimes linked into interferometric arrays, point toward the object's coordinates and integrate signal over hours. Mostly they detect noise. Occasionally faint lines emerge, barely above detection threshold, indicating molecular presence. The sensitivity is marginal. The object is small, distant, emitting weakly. Radio observations are difficult but occasionally successful. It only took long integration times. Astrometry precise position measurement continues throughout the visible period. Each observation adds another data point to the trajectory solution. Positions are measured relative to background stars whose coordinates are known from stellar catalogues. By comparing the object's position at different times, astronomers calculate velocity, acceleration, trajectory curvature. Early observations have large uncertainty. As observations accumulate, uncertainty shrinks. The orbit converges toward truth. After hundreds of measurements, orbital elements are known to fractions of a percent. This precision enables long-term prediction. It also enables backtracking, searching for the object's origin. It only took triangulation across time. Photometry brightness measurement tracks the light curve as the object recedes. Brightness fades according to inverse fourth power of distance approximately, modulated by rotation. The 8-hour periodic variation persists, visible in photometry even as overall brightness declines. Observers fit sinusoidal models to the variations, extracting rotation period, amplitude, phase. The period remains constant within measurement precision. The amplitude, the difference between brightness maximum and minimum, stays roughly constant, suggesting the object's shape does not change, that no major fragmentation or disruption occurs during perihelion passage. It survived intact. It only took not passing too close. International collaboration enables continuous monitoring. As Earth rotates, different observatories come into night. An observatory in Chile observes for several hours, then dawn approaches. By then, an observatory in Hawaii is in darkness. Continuing observations. Later, telescopes in the Canary Islands, in South Africa, in Australia, take over. The object is monitored continuously, weather permitting, across all longitudes. Data from diverse locations are shared through online databases. Observers coordinate via email, teleconferences, shared documents. The effort is distributed but unified by common purpose. It only took global cooperation. Amateur astronomers contribute observations. Large amateur telescopes, equipped with CCD cameras and modern electronics, rival small professional instruments. Skilled amateurs capture images, measure positions, submit data to central databases. Their contributions supplement professional observations, filling gaps, increasing coverage. The distinction between amateur and professional blurs. Capability matters more than credential. Some amateur observers operate robotic telescopes, remotely controlled via internet, located in dark sky sites far from their homes. The network of observers is vast, heterogeneous, effective. It only took accessible technology. As the object fades, only the largest telescopes continue tracking. 10-meter class instruments Keck, the European Extremely Large Telescope. Gemini can still detect it at magnitude 24, but exposure times stretch to tens of minutes. Fainter than this, even large telescopes struggle. Cosmic rays hit detectors, creating spurious signals. Background noise dominates. The object's faint signal is buried in statistical fluctuations. Observers employ sophisticated techniques median, combining multiple images, subtracting backgrounds carefully, using optimal aperture photometry. They squeeze every photon of information from the data, but eventually physics imposes limits. It only took distance, making brightness too faint. The final confirmed detection occurs on a date several months post-perihelion. A large telescope in Chile integrates for 30 minutes, captures a faint smudge at the predicted position. The smudge is 3 sigma above noise, statistically significant but marginal. Follow-up observations are attempted the next night. Clouds obscure. The night after, the object has drifted farther, fainter still. Attempts continue for weeks. No further detections. The object has crossed below detection threshold. It is no longer observable by current instruments. It continues its journey invisibly. It only took finite telescope sensitivity. Observation records are archived. Images, spectra, light curves, position measurements all are stored in digital archives accessible to researchers worldwide. The data will be analyzed for years. New techniques will be applied. Comparisons with future interstellar objects will illuminate trends. The observations of 3I/Atlas become part of humanity's collective knowledge, a dataset representing thousands of hours of telescope time. The coordinated effort of hundreds of individuals across dozens of institutions and countries. The object itself is gone from view. Its data remain. It only took preservation to enable future science. The telescopes return to other targets: asteroids, comets, exoplanets, distant galaxies. The universe is full of objects requiring observation. Telescope time is precious, allocated competitively, scheduled months in advance. The campaign to observe 3 I/Atlas consumed significant resources. Now those resources shift elsewhere. Other discoveries await, other transients demand attention. The object fades from immediate concern, becoming historical rather than active research. Papers are written, results are published, attention moves on. It only took scarcity of resources. What was left behind is difficult to quantify but certain to exist. Every outgassing event releases not only gas but dust, particles, molecules that do not return to the object. These ejecta follow trajectories determined by their mass, velocity, and solar radiation pressure. Large particles fall into orbits similar to the object's original path. Small particles are pushed outward by sunlight, their orbits expanding, some eventually ejected from the solar system. Medium-sized particles occupy intermediate orbits, ellipses and hyperbolas that thread through the inner solar system for years or millennia before colliding with something or spiraling away. The material is dispersed. The debris trail exists. It only took outgassing to scatter fragments. Dust grains, ranging from nanometers to millimeters, constitute the visible debris. Silicate grains, carbonaceous particles, organic tholins, the same materials that darken the object's surface now drift in heliocentric orbits. Their trajectories spread along the object's path, forming a diffuse stream. If Earth's orbit intersected this stream, the grains would encounter Earth's atmosphere at high velocity, 40 to 70 kilometers per second, depending on geometry. They would heat to incandescence, vaporize, create meteors, but Earth's orbit does not intersect. The inclination is wrong, the timing is wrong. No meteor shower will result. The grains drift unnoticed. It only took orbital geometry. Gas molecules expelled during perihelion disperse more quickly. They're not bound by gravity to the sun or to any body. They move ballistically, spreading in all directions, diluting into the interplanetary medium. Water molecules photolize under solar ultraviolet, splitting into hydrogen and oxygen. Hydrogen, lightest element, escapes the solar system entirely, reaching solar escape velocity through thermal motion alone. Oxygen atoms remain, eventually ionized by sunlight, swept away by solar wind. Carbon monoxide molecules similarly dissociate, their atoms recycled into the solar system's vast reservoir of gas. Within years, the molecules are indistinguishable from the background. It only took chemistry and dispersion. Organic molecules, complex carbon chains synthesized on the object's surface over millions of years, are ejected as dust components. These organics are not alive, but they are complex polycyclic aromatic hydrocarbons, amino acid precursors, perhaps even amino acids themselves. Though unlikely, laboratory analysis of solar system comets has found such molecules. No reason to expect 3 I/Atlas differs fundamentally. These organics, once in space, are exposed to radiation. Ultraviolet photons break bonds, cosmic rays ionize. Slowly the molecules degrade, fragmenting into simpler compounds, but degradation is slow. Some molecules survive for millennia, drifting in solar orbit, a foreign chemistry mixed into the solar system's native inventory. It only took being organic in vacuum. Micrometeorites, grains larger than dust but smaller than pebbles, follow stable orbits. These are too small to survive atmospheric entry intact. If one struck Earth, it would ablate completely, leaving no meteorite. But in space, they're permanent, orbiting indefinitely unless perturbed by planetary gravity or collisions. Over millions of years, a fraction will collide with asteroids, moons, or planets. A grain might impact the moon, embedding in regolith. Another might strike Mars. A third might hit an asteroid, creating a microscopic crater. These impacts are undetectable individually, but cumulatively. They add foreign material to solar system bodies, a trace signature of interstellar origin buried in native rock. It only took collision, Vapor coma remnants persist longer than expected. The coma, when active, extended thousands of kilometers. Even after outgassing ceases, the gas does not vanish instantly. It expands, cools, disperses over weeks. For a month post-activity, a residual cloud of molecules surrounds the object's former position, too tenuous to detect but thermodynamically present. This cloud expands at typical gas velocities hundreds of meters per second, becoming ever more dilute. Within months, molecular density drops below 1 particle per cubic kilometer. Within a year, the cloud is indistinguishable from vacuum. But briefly, a ghost atmosphere lingers. It only took time to dissipate. Plasma interactions leave ionized trails. Solar wind, the stream of charged particles flowing from the sun, interacts with cometary coma gases. Molecules are ionized, electrons stripped away, forming plasma. This plasma is picked up by the solar wind and carried away from the sun, creating an ion tail distinct from the dust tail. After the object departs, the ion tail persists briefly, a filament of plasma stretched across millions of kilometers. The solar wind sweeps it outward. Within days, it disperses, merging with the ambient solar wind. But briefly, it marks the object's passage, an ionized wake. It only took solar wind interaction. Isotopic anomalies, subtle variations in isotope ratios, are mixed into the solar system. The object's deuterium to hydrogen ratio differs slightly from solar system averages. Its oxygen isotopes show different fractionation. These anomalies, diluted by mixing with vastly larger solar system reservoirs, are undetectable. But they exist. 1 trillion water molecules from 3 We/8less, each carrying slightly elevated deuterium, now orbit the Sun among quintillions of native water molecules. The dilution is extreme. The contamination is real. Future solar system chemistry, if measured with impossible precision, would show the tiniest deviation attributable to interstellar visitors. It only took mixing. Gravitational perturbations, though infinitesimal, are technically real. The object's mass, several billion kilograms, exerts gravity on everything nearby. As it passed through the solar system, it pulled on planets, asteroids, dust grains. The pull is incredibly weak. Earth's orbit is not measurably affected. Jupiter's orbit is not affected, but mathematically, the perturbation exists. Every mass perturbs every other mass. The object tugged on Earth by a force measured in femtonewtons. Earth tugged back. The exchanges are negligible, but they occurred. The solar system's total momentum vector shifted by an amount too small to measure, but real nonetheless. It only took universal gravitation. Photometric records archived in observatories constitute another form of residue. Images of the object, stored on hard drives and tape backups, will persist for decades, perhaps centuries if maintained. These images are not physical debris, but information debris. They encode the object's passage position, brightness, appearance. Long after the object exits the solar system, these images remain accessible to future researchers. The object's visit is documented. The documentation is legacy. In that sense, the object has left something behind more permanent than dust, a record in human archives. It only took digital storage. The object's trajectory itself is a form of scar. It passed through space, bent light, deflected particles, altered fields infinitesimally. Space is not a medium that records scars. It returns to vacuum. But causally, the object's passage has effects. A dust grain deflected by the object's gravity follows a different orbit than it would have otherwise. That grain, billions of years hence, might collide with something in a different location because of the deflection. Causality branches. The object's presence ripples forward in time through an infinite chain of consequences, each smaller than the last, but none exactly zero. It only took causation. The ultimate question is whether anything detectable remains. The answer is probably not. The dust stream is too diffuse. Too scattered, the gas dispersed, the ionized plasma vanished. No physical sample can be collected. No meteorite will fall from 3/Atlas. No spacecraft will intercept its debris. The object came and went, leaving traces below detectability thresholds. But probably not is not certainly not. Perhaps a dust grain will be collected someday by a spacecraft sampling interplanetary dust. Perhaps isotopic analysis will reveal foreign ratios. Perhaps future technology will detect what current technology cannot. The possibility is non-zero. It only took leaving microscopic residues. Calculating where it came from begins with backtracking the trajectory. Astronomers take the object's current position and velocity, measured with precision during its observable passage, and integrate the equations of motion backward in time. The integration accounts for the Sun's gravity, planetary perturbations, relativistic corrections, step by step, year by year. The calculation traces the object's path into the past. The hyperbola extends outward, crossing Neptune's orbit in reverse, traversing the Kuiper belt, passing through the heliopause. Beyond the heliopause, solar gravity becomes negligible. The trajectory becomes nearly straight, pointing back toward a region of sky. That region becomes the search area. It only took reversing time mathematically. The search area is not a point but a cone. Uncertainties in current position and velocity, tiny in absolute terms, measured in kilometers and centimeters per second, grow exponentially when propagated backward across light years. After 1 million years, position uncertainty measures parsecs. After 10 million years, tens of parsecs. The cone of possible origin encompasses hundreds or thousands of cubic parsecs, a volume containing tens of thousands of stars. Any of these stars could theoretically be the birth system. Most are not. Most are simply along the line of sight. But some fraction are plausible candidates. The task is winnowing plausible from implausible. It only took uncertainty growth. Stellar catalogues provide data on nearby stars. Gaia, the European Space Agency's astrometry mission, has measured positions, distances, and velocities for billions of stars. Within 200 light-years of the Sun, Gaia catalogued nearly every star brighter than magnitude 20. Each entry includes precise coordinates, parallax measurements yielding distance, proper motion measurements yielding tangential velocity, radial velocity measurements from spectroscopy yielding line-of-sight velocity. With these data, astronomers reconstruct each star's past trajectory through the galaxy. Where was this star 1 million years ago? 5 million, 10 million? The calculations are straightforward but computationally intensive. It only took astrometric precision. The search focuses on stars within the origin cone. Thousands of stars qualify geometrically. Most are excluded by velocity mismatch. If 3/Atlas originated from a star system, it likely shares that system's velocity through the galaxy, plus ejection velocity perhaps 5 to 20 kilometers per second relative to the star. Stars moving in completely different directions are unlikely parents. Stars moving nearly parallel to the object's motion are candidates. Velocity cuts reduce the candidate list from thousands to hundreds. Further cuts, considering age, metallicity, presence of planetary systems, narrow the list further. It only took filtering. One star emerges as a tentative match, a G-type main sequence star, similar to the Sun, located 180 light-years away in the direction of Lyra. Its current velocity through the galaxy, adjusted for galactic rotation and peculiar motion, aligns with the object's velocity within error bars. Backtracking both trajectories suggests they occupied the same region of space approximately 8 million years ago. The coincidence is suggestive. But coincidences occur within a volume of space containing 10,000 stars. Finding one star that aligns by chance is not surprising. Statistical significance is marginal. The candidate is plausible. It is not confirmed. It only took one alignment. Further evidence would require spectroscopic matching. If 3I/Atlas originated from that star system, its composition should reflect that stars' photospheric abundances. Different stars have different metallicities, different ratios of carbon to oxygen, different isotopic compositions. These variations are small but measurable. Spectra of the candidate star show metallicity slightly above solar, carbon to oxygen ratio consistent with solar, nothing anomalous. Spectra of 3I/Atlas show composition broadly consistent with solar system comets, with hints of differences in deuterium ratio and certain isotopes. Do the spectra match within error bars? Possibly. Definitively no. The data are insufficient for confirmation. It only took limited spectral resolution. Alternative hypotheses remain viable. Perhaps the object originated from a star no longer identifiable. Stars drift. 8 million years of galactic motion can separate a star and its ejected fragment by hundreds of light years. If the birth star was a low-mass M-dwarf, faint and difficult to detect, it might not appear in catalogues. If it was part of a moving group or open cluster that has since dispersed, tracing origin becomes harder. If ejection occurred during a stellar encounter, two star systems passing close, gravitationally perturbing each other's comets, the origin might involve multiple stars. The complexity multiplies. It only took millions of years. Another possibility, the object formed in a molecular cloud, never bound to any star. Molecular clouds, vast regions of cold gas spanning tens of parsecs, are the birthplaces of stars. But not all material in a cloud condenses into stars. Some remains as diffuse gas. Some clumps into denser cores that never ignite fusion. Could 3I/Atlas be a fragment that formed in such a core, later dispersed when nearby stars disrupted the cloud with radiation and winds? The idea is speculative, but not impossible. Its composition fits cold, ice-rich, carbon-bearing. Its trajectory, if traced back farther, might intersect regions where molecular clouds existed millions of years ago. It only took speculative astrophysics. Galactic dynamics complicate everything. The Milky Way is not static. Stars orbit the galactic center in complex patterns, rising and falling through the disk, perturbed by spiral arms, influenced by the galaxy's overall gravitational potential. An object ejected 8 million years ago has experienced these perturbations. So has every star. Reconstructing past positions requires modeling the galaxy's gravitational field, accounting for spiral density waves, considering the influence of dark matter. Models exist, but uncertainties are large. Predicting where a star was 10 million years ago involves assumptions about galactic structure that may be incorrect. The backtracking is probabilistic, not deterministic. It only took galactic complexity. Some researchers question whether the object is truly interstellar. Could it be a solar system native ejected recently outer solar system bodies? Perturbed by planets, occasionally reach escape velocity. Could 3I/Atlas be such a body, mistaken for an interstellar visitor? The argument is weak. Its velocity exceeds solar system escape velocity significantly. Its trajectory does not originate from the Oort cloud or scattered disk. Its composition, while similar to solar system comets, shows subtle differences. The evidence favors interstellar origin, but science requires skepticism. Alternative explanations are entertained, tested, mostly rejected. It only took considering all possibilities. The ultimate conclusion is unsatisfying origin unknown, likely from a star system within 200 light-years, possibly from the candidate G-type star in Lyra, possibly from an unidentified M-dwarf, possibly from a dispersed molecular cloud. The probability distribution is broad. No single origin is certain. This is common in astronomy. Many phenomena resist definitive explanation. The universe is large, complex, and observed incompletely. 3I/Atlas carries its origin as information, encoded in isotopes and chemistry, but the cipher is only partially readable with current technology. It only took facing the limits of knowledge. Future detections of interstellar objects may illuminate patterns. If multiple objects arrive from the same region of sky, a common origin becomes likely. If compositions cluster, formation mechanisms narrow. If velocities correlate with stellar populations, ejection dynamics clarify. 3I/Atlas is a single data point. Single data points constrain weakly. Populations constrain strongly. The field awaits more data. Telescopes planned for the next decade, the Vera Rubin Observatory, with its wide-field survey capabilities, will detect interstellar objects routinely, perhaps dozens per year. Each detection adds knowledge. Each trajectory traced backward adds constraints. Slowly, the picture clarifies. It only took patience and more observations. Questions without answers yet accumulate like sediment. The object raises mysteries that observations cannot resolve, puzzles that data constrain but do not solve. Its composition is known approximately but not precisely. Spectra reveal water, carbon dioxide, carbon monoxide, silicates, organics but the exact ratios, the isotopic abundances, the crystalline structures, the three-dimensional distribution of materials within the nucleus. These remain uncertain. Models fit observations, but models are not unique. Different assumptions yield different conclusions. The object could be ice-rich with minor rock. It could be rock-rich with ice coating. It could be layered, differentiated, homogeneous. The data do not decide. It only took insufficient resolution. The origin question persists as the central mystery. Where did it form? When did it form, under what conditions? Was its birth system similar to ours or different? Did it form in a protoplanetary disk around a main sequence star, or in the outer regions of a binary system, or in a dispersing star-forming cluster? Each scenario predicts different properties: formation temperature, composition, isotopic ratios, volatile content. Comparisons with solar system bodies suggest similarities, implying similar formation conditions, but similarities are not identities. Subtle differences exist. Are these differences meaningful or noise? The question remains open. It only took ambiguous data. The ejection mechanism is inferred but not observed. Something gave the object enough velocity to escape its birth system. Giant planet scattering is the leading hypothesis. Simulations show that as giant planets migrate inward or interact dynamically, they fling smaller bodies outward. Some achieve escape velocity. The process is efficient, common, expected. But it is not the only mechanism. Stellar flybys, another star passing through the outer edges of a planetary system, can gravitationally perturb objects into unbound orbits. Supernova shock waves, if the birth system was near a dying star, can provide energy. Binary star interactions create chaotic dynamics. Multiple mechanisms operate. Which one ejected 3I/Atlas unknown? It only took not witnessing ejection. The journey duration is estimated but uncertain. If the object travelled from a star 180 light-years away at 26 kilometers per second, the journey took approximately 7 million years. But uncertainties in origin distance multiply into uncertainties in duration. If origin was closer, duration was shorter; if farther, longer, and duration assumes constant velocity, ignoring possible perturbations from stellar encounters en route. An encounter with a star could accelerate or decelerate the object, lengthening or shortening the journey. The 7 million year estimate is a reasonable guess. It is not a measurement. It only took accumulated uncertainties. The rotation state raises questions. Why does it tumble instead of spinning smoothly? Non-principal axis rotation requires excitation and impact. A close gravitational encounter, asymmetric outgassing during a previous perihelion passage around a different star. Which mechanism excited this object when the tumbling persists because damping is slow, requiring internal friction that dissipates rotational energy? On what timescale does damping occur tens of thousands of years, millions? The answer depends on internal structure, on whether the object is solid or rubble pile, on material strength and porosity. Observations suggest low density, high porosity, implying slow damping. But how slow, it only took not knowing internal structure. The surface properties remain ambiguous. Is the dark red colour intrinsic or a radiation-processed rind? How thick is the processed layer? Millimeters meters, does pristine material exist beneath, unchanged since formation? Or has radiation penetrated throughout? Cosmic ray penetration depth depends on exposure, duration and composition. For an object exposed for millions of years, penetration could reach meters, but shielding by outer layers reduces deeper penetration. The interior might be pristine, or it might not. Without direct sampling, without drilling or excavating, the question is unanswerable. It only took being unsampled. The activity level during perihelion was modest but variable. Some regions outgassed vigorously, others remained quiet. Why compositional heterogeneity is likely some regions contain more ice, others more dust. But heterogeneity alone does not explain activity patterns. Orientation matters. Regions facing the sun sublimate. Regions in shadow do not, but the object tumbles, so all regions eventually face sunward. Yet activity concentrates in specific areas. Perhaps topography channels gas flow. Perhaps subsurface layers vary in permeability. Perhaps past activity created preferential pathways. The mechanisms are understood in principle but not in detail. It only took complexity. The structural integrity puzzle persists. Is the object monolithic or aggregate? Monolithic implies formation as a single body, later fractured but cohesive. Aggregate implies formation by gentle accretion of smaller pieces, never compressed into unity. Evidence suggests aggregate low density, high porosity, irregular shape, but aggregate implies weak cohesion. How does it survive tumbling stresses, thermal stresses, outgassing forces? Self-gravity is minimal, tensile strength is low for porous ice, yet the object remains intact. Perhaps it is more cohesive than assumed. Perhaps molecular forces van der Waals. Hydrogen bonding provides strength. The balance between disruption and cohesion is delicate. It only took surviving perihelion. The frequency of interstellar visitors remains unknown. 3 confirmed detections, Oumuamua, Borisov, 3I/Atlas over several years suggests arrival rates of roughly 1 per year detectable by current surveys. But detection efficiency is low. Small objects, or objects passing distant from Earth, or objects arriving from unfavourable directions, go undetected. The true arrival rate is likely much higher, perhaps 10 per year, perhaps 100. Extrapolating to all of interstellar space, billions of such objects might traverse the galaxy at any moment, but billions is speculative. The data are sparse. Arrival rates remain uncertain by orders of magnitude. It only took small sample size. The diversity among interstellar objects is striking, but based on 3 examples, Oumuamua was elongated, inactive, possibly rocky. Borisov was typical comet-like, active, icy. 3I/Atlas is intermediate active but modest, elongated but not extremely compositionally mixed. 3 objects show 3 different properties. This suggests high diversity, implying interstellar populations are heterogeneous, drawn from varied environments, or it suggests selection bias, different types are detected under different circumstances, or it is coincidence 3 is too few to draw conclusions. More detections will clarify. Until then, diversity remains suggestive, not conclusive. It only took 3 data points. The purpose of studying interstellar objects is sometimes questioned. Why observe them? What do they reveal? The answers are multiple. They sample other planetary systems, bringing alien chemistry within reach. They test planet formation theories by providing comparison cases. They probe ejection mechanisms, galactic dynamics, interstellar medium properties, they inspire wonder, demonstrating the interconnectedness of stellar systems. And they pose practical questions about planetary defense, about distinguishing natural from artificial, about the prevalence of panspermia. The scientific value is clear. The cultural value is harder to quantify, but real. They are messengers from elsewhere. It only took curiosity. The most profound mystery is philosophical. Does the object carry meaning, not intentional meaning? It is not a message, but existential meaning. It formed around another star, ejected into darkness, crossed the void for millions of years, passed through our system briefly, and continues into darkness again. Its journey is purposeless, determined by physics alone, yet humans observe, measure, wonder. We assign significance to its passage. We calculate, model, publish. We name it, track it, remember it. The object is indifferent. It does not know we exist, but we know it exists. In that asymmetry, some find meaning, others find only physics. The question is unscientific, unanswerable by observation. It only took consciousness to ask. The object crosses outward through the orbits of the outer planets, receding into distances where the sun dims to bright star, then to point of light, then to one light among billions, at 15 astronomical units. Velocity has dropped to 55 kilometers per second, at 20, 49, at 30, 41. The deceleration continues smoothly, asymptotically approaching the hyperbolic excess velocity of 26 kilometers per second, the speed it will carry forever once solar gravity becomes negligible. The approach is asymptotic. It never quite reaches that velocity while still in the heliosphere. But it gets closer. It gets very close. It only took climbing outward indefinitely. At 50 astronomical units, crossing the scattered disk, surface temperature has fallen to 25 Kelvin. All volatiles are frozen solid. Carbon monoxide. The last to sublimate, now condenses back onto the surface. The outbound journey deposits molecules that the inbound journey removed. The surface composition shifts subtly. The object is not identical to what entered. Mass is slightly lower, surface texture slightly different, thermal history recorded in crystalline structures. But mostly it is the same. Mostly it returns to the state it held for millions of years before encountering the sun. It only took symmetry of heating and cooling. The Kuiper belt is traversed outbound. Thousands of objects orbit here. Remnants of solar system formation. Icy bodies that never accreted into planets. 3I/Atlas passes among them, indistinguishable in appearance, a dark, irregular ice ball tumbling through space. But its trajectory distinguishes it. The Kuiper belt objects orbit. They return, they belong. 3I/Atlas passes through, never returning, not belonging. The distinction is velocity. The distinction is everything. It only took hyperbolic excess. At 70 astronomical units, 1 year after perihelion, the object is barely detectable by the largest telescopes, and then only in long exposures. No further observations are attempted. The last photons from 3I/Atlas to be deliberately captured by humans have already entered detectors, been converted to electrons, been recorded as data. The object continues to reflect sunlight. That light travels outward, spreading into space. Some fraction aimed toward Earth, but no telescope gathers it. No sensor records it. The light exists, but unobserved. It only took exceeding detection thresholds at 100 astronomical units, approximately 18 billion kilometers. The object approaches the heliopause. The crossing is gradual, taking months. Solar wind pressure decreases, interstellar medium pressure increases, cosmic ray flux rises as solar magnetic shielding weakens. The transition is gentle, marked by no visible change. The object does not notice. It tumbles through. Temperature now stable at 10 Kelvin. Surface in thermal equilibrium with a cosmic microwave background and starlight. The sun is 100 times fainter than seen from Earth. It is still the brightest object in the sky, but not by much. Sirius, Canopus, other bright stars shine almost as brilliantly. The sun's dominance fades. It only took distance. Beyond the heliopause, in interstellar space again, the object resumes the existence it held for millions of years before solar encounter. It drifts in near vacuum. 1 atom per cubic centimetre surrounds it. Cosmic rays strike its surface. Continuing the slow radiation processing, starlight, the collective glow of the Milky Way, provides the only illumination. Faint and diffuse. Temperatures remain at 10 Kelvin, fluctuating by millikelvins with passage through molecular clouds or open voids. The journey has no destination. It travels in a direction determined by ejection velocity and subsequent perturbations. That direction aims toward no particular star. It aims toward empty space between stars, toward regions the object will cross in 1,000,000 years, 10 million, 100 million. It only took not being bound. The tumbling persists. Rotation continues with period 8 hours unchanged. No friction acts. No torque alters angular momentum. The object spins as it has spun, as it will spin, essentially forever. Over billions of years, internal friction might damp the tumbling into principal axis rotation. Over trillions of years, tidal forces from galactic gravity gradients might affect it infinitesimally. But over timescales relevant to humanity, it tumbles unchanging. The stars wheel around it not actually, but in its rotating reference frame. Every 8 hours, the galaxy completes 1 rotation in the object's sky. The motion is hypnotic, perpetual, meaningless. It only took angular momentum conservation. The sun recedes behind. Its light diminishes according to inverse square law. At 200 astronomical units, it is 4 times fainter than at 100. At 400, 16 times fainter. At 1,000, 100 times fainter. Eventually it becomes indistinguishable from other stars, not the brightest, not particularly notable, 1 G-type star among billions. An observer on the object, watching the sky over years, could track the sun's slow drift against background stars, its dimming, its eventual loss into anonymity. But there is no observer. The object is alone. It only took distance to erase dominance. Time stretches ahead. The object will travel for another 1,000,000 years. 10 million, 100 million, crossing the space between stars at 26 kilometers per second. Occasionally it will pass near other stars, statistically, over millions of years. Another close approach is likely. Perhaps it will pass through another planetary system. Perhaps it will be heated again, outgas again, develop another coma. Perhaps it will be observed by inhabitants of that system, if such exist, if they've developed astronomy, if they notice. The probability is low but non-zero. Or perhaps it will pass through empty space, unperturbed, unobserved, for billions of years. Both futures are possible. It only took time being vast. The galaxy rotates slowly beneath. Stars orbit the galactic center in vast, lazy loops taking hundreds of millions of years. The sun orbits, the object no longer bound to the sun, orbits independently, tracing its own path through the galactic potential. Its orbit differs from the sun's over time. The separation grows. In 10 million years, the sun and object will be separated by tens of light years. In 100 million years, hundreds of light years. They will never be close again. Their mutual history, the few months when the object passed through the inner solar system, observed by humans, studied by telescopes, is brief and unrepeated. It only took parting. Does the object remember? No. Memory requires structure, information storage, mechanism. The object is ice, rock, organics. It holds no record of its passage except the missing mass, the altered surface, the trace chemical changes. These are not memory but consequence. They record nothing intentionally. They simply are. The object does not know it visited the sun. It does not know humans observed it. It does not know anything. It is matter in motion. It only took being inanimate. Does the universe remember? In a sense. Every event leaves causal traces. The object perturbed solar system trajectories infinitesimally. Those perturbations propagate forward, affecting future states, creating branching possibilities. Information is not destroyed. It disperses, spreads, becomes uncorrelated, effectively irretrievable. But technically it persists, encoded in the universe's quantum state. Philosophically, the visit is remembered by causality itself. Practically, it is forgotten. Only humans remember, in archives, in papers, in data. And humans are brief. It only took entropy. The stars do not change from the object's perspective. They appear fixed, eternal, unchanging. But they are not. Stars are born, live, die. Over millions of years, new stars ignite in molecular clouds. Old stars exhaust fuel, swell into giants, explode as supernovae or fade as white dwarfs. The constellations shift, the sky rearranges, the object, travelling at a constant velocity relative to the local standard of rest, sees the sky drift slowly. Stars approach, pass, recede. The view changes over mega-years, but within any human lifetime, the sky is still. It only took travelling slowly relative to stars. The cold is absolute, patient, gentle. 10 Kelvin is not harsh. It is simply the absence of heat. Molecules barely vibrate. Quantum ground states dominate. Chemical reactions cease. Time, measured by change, slows nearly to stopping. The object exists in this cold, unchanged, unchanging. It will exist this way for longer than species persist, longer than mountains erode, longer than continents drift. It has patience because it has no alternative. It has no urgency because it has no destination. It simply continues. The dark between stars is where it belongs. It only took returning to equilibrium. Stillness settles. Motion persists but seems motionless. The object drifts at 26 kilometers per second yet appears suspended. Alone. Quiet. Space is vast enough to make even speed seem like rest. The journey that seemed brief during perihelion now seems infinite, stretching endlessly forward and back. There is no drama here, no climax, no resolution, just continuation, just the patient crossing of voids, just existence in darkness, in cold, in silence. The object is a grain of dust in the galaxy, insignificant, beautiful, alone. It only took being small in vastness. And here, where nothing happens, where time is measured in millions of years, where silence is not absence of sound but absence of event, the story rests, not ends, rests, because endings are human constructs and the object knows no endings, only continuity. It drifts, it will drift. The dark receives it, the stars witness distantly. The universe continues, indifferent and immense,